Okay, moving on to section 1.6, we're going to look at solving linear inequalities. So we finished up working with linear equations. Now we're going to look at linear inequalities. So remember, inequalities, we're comparing two sides with less than, greater than, less than, equal to, or greater than, equal to symbols. So in the comparison of two sides, in which one is smaller or larger, or again, we can include equality also with those. With that said, solving linear inequalities is no different than solving a linear equation. All right, we're looking at solving for the unknown of the variable, trying to get that unknown by itself. With that said, we have the addition property of inequalities, which is the same thing as the addition property of an equation, in that you can add or subtract any number you want on both sides of inequality, and it will not affect the inequality. All right. Now, where you have to be careful is with the multiplication property of inequality. Multiplication property of inequalities says if you multiply or divide both sides by a positive number, nothing changes. So you can see here for some number c greater than 0, when we multiply both sides by that number c, it's still a less than problem. Now, it changes when we're dealing with a negative. So if c is a number less than 0, or it's negative, and you take this inequality of a less than b, just for example, if we multiply both sides by that negative number, right, it changes and reverses the inequality symbol. So multiplying or dividing by a negative number reverses or flips the inequality sign. Right? And we can show that in an example. Right? If you look at, just to show this properly, let's write an example over here on the side. For example, we all know that negative 2 is less than 3. Right? There's a true inequality. Right? And this is, again, it doesn't have to be, I keep using less than as the problem. We could write it as a greater than problem. We all know that negative 3 is greater than what? Negative 5, right? We can look at two negative numbers. Now, here's the thing. When I introduce multiplication property of inequalities, if I were to multiply both sides by a positive number, say we times both sides by 2, that would imply negative 6 is greater than negative 10, which it is. That's true. Now, if we were to change that up, though, right, if we were to do a negative 2, right, let's put a negative in here. If we multiply both sides by negative 2, no longer is that the case. Right now, we would have a positive 6, right, and we leave the greater than symbol. Negative 5 times negative 2 is positive 10. Well, 6 is not greater than 10, right? It's not true. You got to flip it. So anytime you multiply or divide by a negative, you need to remember to reverse that inequality symbol. So again, reverse the inequality symbol, right, when you're dealing with a negative number. So as an example of that. So let's take a look at some inequalities to solve that show up here in this section. Now, as we look at these linear inequalities, these are all linear inequalities with one variable. So we're solving for x, right? We want to get x by itself. Now, we have a couple of x terms in this problem. So our first step is to group the x terms together. So again, we treat it no different than a linear equation. We got to isolate x on one side of the inequality by itself. So I'm going to go ahead and move the x terms together. And while we're at it, let's go ahead and move the minus 7 over to the other side. We can go ahead and add a 7 on both sides. And as we do that, right now our inequality is set up like we want it. We've got the x terms together on the left side by themselves. Now this is still a greater than inequality. Nothing has changed. We don't reverse anything. We have not multiplied or divided by negative. Right? We can add and subtract, which is what we've done, the addition property of inequalities. So right now we have 2x greater than 16. Well, our last step, right, would be to divide out the 2 on both sides. As we do that, we get x greater than 8. Right? So our solution set is all values of x larger than 8. So when is 5x minus 7 greater than 3x plus 9? For all the x values greater than 8. Now, with that said, I want to talk about different forms for our solution set. All right, we're going to state this statement of solutions. And right now, I want to graph in the solution set. Say it asks for the graph of the solution set. As we do that, let's go ahead and build our x line. So we're looking at all real numbers x, negative infinity to positive infinity. As we place 8, our critical value, on here, to be greater than 8 means we don't want to include 8. So I'd put an open circle on that. And then I'd shade in all the real numbers larger than 8, right? So there's a graphical representation of the solution set. There's every real number value of x greater than 8. 8.01, 8.5, 9, 10, 11, 12, all the way to infinity. Now, our preferred form, and most of the time you're going to see it ask for an interval notation. So, of course, our interval notation would be a parentheses on 8, comma, infinity. So bracket means we want it, parentheses means we don't. Now, I do like to take the time and check it. And again, you can check it by plugging in numbers, right? One on the inside and one outside to see if it works. You can also go to your calculator and you can look at intersection method, right, and see that take place too. So that's one thing to look at since you have your TI, a quick check graphically. Let's go to our calculator. Let's pull up here. I'm going to go back to what we talked about in our previous section where we did the intersection method. Let's graph the two sides of this equation. I'll show you with intersection. And then we can show it with zero method also. All right, on this graph, all right, if you're looking at the graph of 5x minus 7, which is what we want to look at to be greater than 3x plus 9, all right, we graph that in our inequality. So let's go ahead and let's clear it out. Let's do the zero method, get a better picture. Take 5x minus 7. Let's set it equal to 0. So we'll minus the 3x over, and then we'll minus the 9. Get a little better picture, which is doing the zero method. So I'm going to store it all in on one side. So again, that's taking my inequality that we were given, putting it all in on one side. And now when I graph this on a standard window, right, you can see when this graph is greater than 0. So here's the zero method. So here's again your 0 at x equal to 8. So if all the values greater than 8, right, that's when we get our values here being greater than 0. All right, so again, you can see that, of course, in your table also. So when you start getting your values greater than 0, for all the values greater than 8. That's the zero method too, just to tie it in what we've talked about already. You can see it graphically, right, what we'd look at there on our calculator. Let's solve algebraically. This next example, here in example B, we've got a linear inequality, one variable. Let's solve for x. With that said, now we have some simplifying to do in our first step. So step 1, an example like this one, would be to go ahead and distribute, clear the parentheses. So let's go ahead and do that. We got negative 13 plus 5 times 2, which is 10, plus 5 times negative x, which is negative 5x, less than or equal to, this time we have equality, less than equal to problem, less than equal to, now let's distribute, negative 3 times x, negative 3x, negative 3 times 7 is negative 21. So I've cleared my parentheses, I've distributed, so apply the distributive property. All right, and we make a note there of what we just did in that step. And then we'll combine our like terms. Now we have a couple of constant terms here. So as we're adding those up, we get negative 3. So I got negative 3 minus 5x less than or equal to negative 3x minus 21. Right, combining the like terms. So we can make a note of what we did in that step. Now we got to get the x terms together. So let's go ahead and group them on one side. So let's use the addition property of inequalities. Let's add a 3x to both sides. And let's go ahead and take care of the constant. Let's go ahead and move the minus 3 over. So we'll go ahead and add a 3 to both sides. As we do that, right, we get what we want as far as the arrangement of our inequality. We get the x term together on the left side by itself. Now, negative 5x plus 3x is negative 2x. Nothing has changed here. We have multiplied divided by negative, so that's still less than or equal to. Negative 21 plus 3 is negative 18. And now as we divide out our coefficient, as we divide out the negative 2 on both sides, you got to stop yourself. So at this point, we're going to have to reverse. And the reason we're going to have to reverse is because we're dividing by a negative number. So x is now greater than equal to 9. So again, you got to flip it. So you got to flip, right, or reverse the inequality symbol because of the negative. All right, multiplying by negative, we got to flip. So again, we make that note here on the side. Multiply or divide by a negative number implies reverse inequality symbol. And we've got our solution set stated right now. So if you want, we can go ahead and graph, right, the solution set. So we can go ahead and take, let's put the graph here beneath it. So graphing in the solution set, here's all real numbers x, negative infinity to infinity. And our critical value is 9. Now 9 is a solution. So instead of an open circle, we'll put a closed circle or a bracket. Bracket would be we want to include it. The same thing with open circle, you use a parenthesis if you wanted. And then our preferred form, let's put in the interval, which needs a bracket on 9 to infinity. There's a list of every real number value, right, that satisfies this inequality. All right, so again, that's looking at linear inequalities with one variable. And you check it. Like I said, you could graph it, use the zero method again. Again, wouldn't take long to check. So again, that's solving linear inequalities with one variable. All right, let's add to it a little bit. Let's move on to our last topic in this section, which is compound inequalities, which is joining up two inequalities with the word and or the word or. In the math, and or, all right, those two words mean totally different things, right? And in math means, we think, intersection. What satisfies both, right, to make a solution? We have to satisfy both restrictions. Or it can be either one to make a solution. When we see and inequalities with compound inequalities, most of the time we'll see it probably written as a three-part inequality, where we have an expression of x bounded between two numbers, two restrictions. So 5x minus 2, for example, being greater than or equal to negative 4. You always read from the variable part, so it's greater than or equal to. And at the same time, that same expression of x needs to be less than 7. So there's two restrictions on x to find the solution. So let's take that and look at it here, an example. So let's do example A. So we got negative 5 less than or equal to 1/2, 3x plus 1, less than 7. So when I'm looking at solving this inequality, the first thing I'm going to do in solving that, worst thing I would do is clear out the fraction. I'm going to use the multiplication property of inequalities. I'm going to multiply everything by 2. Right, I'm going to clear the fraction. Right, I don't like fractions, so I'll get rid of them. So again, we do that with our LCD. We only have one fraction, so our LCD is that denominator of 2. So we multiply, again, everything by 2. So as we do that, what happens? The 2's divide out. So we get rid of that fraction. Now nothing changes with the inequality symbols because, again, we're multiplying by positive 2. So negative 5 times 2 is negative 10, still less than or equal to symbol. But now I've got 1/2 of 2, which is 1, so all we're left with in the middle is just 3x plus 1, right? Because we've gotten rid of what? We've gotten rid of the fraction. So we've gotten rid of the 1/2 by multiplying by 2. And then we got on the right side of this three-part inequality a 7 times 2, which is 14. So that cleared out the fraction, multiplying by the LCD. Now as we're solving for x, we notice x is in the middle, so we want to get it by itself. So our next step, I'm going to get rid of the constant term. That would be our next step to isolate x. So we need to subtract the 1, and we got to do it to all three parts, right? The addition property of inequalities. We've got to do it to both sides of the inequality. So there's all three parts in this one. Now as we do that, nothing changes with the inequality symbols. We're not multiplying and dividing by negative. We're adding a negative. So nothing changes there. But with that step, we're now down to negative 11, and in the middle, 3x, less than 13. And then our last step, divide out our 3. And we got to do it with all three parts. Now this is a positive 3, so nothing changes, right? So the inequality symbols stay the same. So we end up with what? Negative 11 thirds on the left side of the three-part inequality, and x here in the middle, and then less than 13 thirds. So there's a statement of our solutions. Now I like to break that up. So this says that x must be greater than or equal to negative 11 thirds, and at the same time, x must be less than 13 thirds. So there's a statement of our solutions. There's two restrictions on x. It's got to be greater than or equal to negative 11 thirds and less than 13 thirds, which is 4 1/3, right? If you want to write it as a mixed number. And of course, negative 11 thirds is negative 3 2/3. Now let's graph that. So let's look at this graphically. Let's go ahead and graph in the solution set. So as we look at our graph, right, we've got all real numbers x. Here's negative infinity to positive infinity. Here's negative 11 thirds. Here's 13 thirds. Greater than, equal to, and less than. So I'm going to go ahead and put my closed circle and open circle. Now, greater than or equal to negative 11 thirds, we would usually shade all the way to positive infinity. But here's the difference. With it being a and problem, we've got to be bounded between the two numbers. Got to satisfy both. So again, and must satisfy both at the same time to be a solution. So you can see that would be the overlap. If you were to graph these separately, this would be the overlap of the two graphs. But there it is, our graph of that solution set. And of course, our preferred form, let's go ahead and write in the interval, bracket negative 11 thirds to 13 thirds with a parentheses. So there's our solution set in interval form. All right? Our preferred form. All right, let's take that. Let's go to example B. Take a look at our next one here. And example B is we solve this next three-part inequality. In B, I've got a three-part inequality with our x or unknown in the middle of the three parts. As I'm solving that for x, the first thing I'm doing, I'm going to go ahead, there's no fractions to clear in this one. I'm going to go ahead and get rid of the 3 that's added to the x term. So I'm going to apply the addition property of inequalities. Nothing changes with the inequality symbol. We haven't multiplied or divided by a negative, so the symbols stay the same right now. Now, as we look at this, we can see now we're down to negative 2x in the middle. Well, now we got to divide out the negative 2. Now, this is the multiplication property of inequalities. We multiply or divide by a negative, you must reverse or flip the inequality symbol. So now we got to change them. So these must reverse. So we'll do that beneath it. So as we look at what it simplifies down to, we've got 1, and this is now the greater than symbol, must reverse it. And then we got x here in the middle, and then we got a flip, we must reverse negative 3. All right, so there's our statement of solutions. So again, make sure you reverse them, right? So with that said, we got to reverse the inequality symbols whenever we multiply or divide by a negative. So again, make sure you reverse them and flip them. Reverse. right, because of the negative. Now, as we state our solutions, let's go ahead and do a statement. So what does this read? So this reads what? X greater than -3, and at the same time, X must be less than 1 to be a solution. Right? So again, you read from the variable out. So read from the middle. So that's X less than 1. So there's a statement of our solutions. And then we'll go ahead and graph them. So as we graph in the solution set, here's all real numbers X, negative infinity to infinity. Let's place our two critical values on here. Greater than, less than, we need open circles, no equality on these. And we're bounded between the two numbers, an and problem. As we look at that as an interval, right, our interval is parentheses -3 to 1 parentheses. So there's our interval notation. So again, solving that compound inequality, that and inequality. Let's take a look at our last one. In our last example, we've got 5x plus 11 less than or equal to -4, or, so there's a or problem, that same expression of x, 5x plus 11, greater than or equal to 4. Now, this is not a three-part inequality. Don't try to bound it between two numbers. It's a or problem. These are totally different ends, less than or equal to -4, greater than or equal to +4. All right, there's nothing in between that we're looking for like we do with and problems. There is no overlap in these two, and you'll see that when we graph it in a little bit. So if we'd have put the word and, there wouldn't even be a solution to this compound inequality. Now, with that said, as I'm trying to solve it, we're going to get x by itself. So let's go ahead and subtract 11. Let's move it over. As we do that, we get what? We get 5x. Again, those cancel out. Less than or equal to -15. Or over here, as we subtract the x on both sides, 5x is greater than or equal to -7. And then our last step, right, would be divide out the coefficient. Now, this time we're not dividing by a negative number, right? We're dividing by a positive number, so nothing flips or changes. So as far as our solution set goes, we got x less than or equal to -3, -15 divided by 5, or x greater than or equal to -7/5. So there's a statement of our solutions. So let's go ahead and look at it graphically. Let's put in our graph too. What's the graph our solution set going to look like? Here's all real numbers x, negative infinity to infinity. We got -3 as a critical value. We got -1 2/5 or -7/5 as a critical value. Now, less than or equal to means we got to include -3. And less than or equal to, we go all the way to negative infinity. So all real numbers less than or equal to -3 are a solution. Or all numbers greater than or equal to -7/5. So as we go in there and look at that, right, as a graph, shading in every number to the right all the way to infinity. So again, there's infinite solutions. Pick a number out of either of those shaded regions, plug it into this original inequality. It's going to satisfy one of those two. Not both. There's no overlap. No number would satisfy both at the same time. But we don't have an and problem. This is a or problem. All right, let's move on to our interval. Our interval, we got two intervals. We got all values less than or equal to -3. So negative infinity, -3, the bracket. And in math, we like to use union. Union is or. Or all x values greater than or equal to -7/5 to infinity. So remember, union is the or symbol. And in math, if you want to think about it, and is the intersection symbol. So again, there's an abbreviation for and also. And is the upside down union symbol, intersection. So looking at it, you see again, right, your solution set. So again, that's a compound inequality. You've seen both types, right? You've seen the or and the and inequalities. So again, you can practice some more in your online assignment. But again, that's in your homework. You can work at some just like these. Okay? So I hope that helps you with section 6.